Imagine being born on a spacecraft hurtling through the cosmos at incredible speeds, living your entire life among the stars and dying light years away from Earth, having witnessed wonders that no human in history has ever seen. The question isn't whether we can travel to distant worlds in a single human lifetime, but how far we could actually go and what cosmic destinations might be within our reach. Today, we are revealing the cosmic distance that NASA doesn't want you to know exists. And here's a question for you. If you could only visit one location in the entire cosmos before dying, where would you choose and why? Drop your answer in the comments below. I will pin the most creative answer. Now let's begin. The human lifespan sets a fundamental boundary on our cosmic ambitions. With current life expectancy hovering around 80 years in developed nations, and even optimistic projections of life extension technologies pushing that to perhaps 150 years, we have a finite window to traverse the vast emptiness between stars. But here's where physics becomes both our greatest limitation and our most powerful ally. The nearest star to our Sun, Proxima Centauri, sits 4.24 light-years away. At the speed of our fastest spacecraft ever built, the Parker Solar Probe, which will eventually reach speeds of 200 kilometers per second, the journey would take over 6,000 years. That's roughly 80 human lifetimes. Clearly, our current propulsion technology isn't going to get us to even our nearest stellar neighbor within a single human lifespan. But what if we could go faster, much faster? The laws of physics don't forbid high-speed travel, they just make it incredibly challenging. As we approach significant fractions of the speed of light, something magical happens. Time dilation kicks in. This isn't science fiction, it's Einstein's special relativity in action. The faster you travel, the slower time passes for you relative to the rest of the universe. Let's run some numbers that will blow your mind. If we could build a spacecraft capable of reaching 90% the speed of light, the journey to Proxima Centauri would take about 4.7 years from Earth's perspective. But here's the kicker. Due to time dilation, only about 2 years would pass for the travelers. They could reach our nearest stellar neighbor and still have most of their lives ahead of them. Push that speed to 99% of light speed, and the time dilation effect becomes even more dramatic. The journey to Proxima Centauri would feel like just 7 months to the travelers, while nearly 5 years pass on Earth. Suddenly, interstellar travel within a human lifetime doesn't just become possible, it becomes routine. But why stop at our nearest neighbor? At 99% light speed, the entire galaxy becomes accessible within a human lifetime from the traveler's perspective. The galactic center, 26,000 light-years away, would feel like a journey of just 3.5 years to someone aboard such a spacecraft. The Andromeda Galaxy, our nearest galactic neighbor, at 2.5 million light-years distant, would subjectively take only 35 years to reach. This is where the cosmic perspective becomes truly humbling and inspiring. We are made of stardust, literally forged in the nuclear furnaces of ancient stars that lived and died billions of years before our sun was born. The carbon in our bodies, the oxygen we breathe, the calcium in our bones, all of it was created in stellar cores and scattered across the cosmos by supernovae. In a very real sense, we are the universe becoming aware of itself, and our desire to explore the cosmos is the universe's way of understanding its own vastness. The challenge, of course, lies in actually achieving these incredible speeds. Conventional chemical rockets, like those that took us to the moon, can only accelerate spacecraft to tiny fractions of light speed. The space shuttle's maximum velocity was about 8 kilometers per second, less than 0.003% of light speed. Even our most advanced ion drives, which can operate for years and gradually build up impressive velocities, top out at speeds that would still require tens of thousands of years to reach the nearest stars. Nuclear propulsion offers our first glimpse of truly high-speed interstellar travel. Project Orion, conceived in the 1950s and 60s, proposed using nuclear explosions to propel spacecraft. By detonating nuclear bombs behind a massive pusher plate, such a craft could theoretically reach 3 to 5% of light speed. While this might sound modest, it would reduce the journey to Proxima Centauri to less than a century, still longer than a human lifetime, but getting closer to the realm of possibility. Fusion ramjets represent an even more ambitious approach. These theoretical spacecraft would scoop up hydrogen from the interstellar medium and use it as fuel for fusion reactions, potentially allowing them to accelerate continuously throughout their journey. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, could theoretically reach significant fractions of light speed, making interstellar travel within a human lifetime genuinely possible. But perhaps the most mind-bending propulsion concept is the photon rocket, a spacecraft that achieves thrust by ejecting pure light. While the thrust would be incredibly small, a photon rocket could theoretically accelerate indefinitely, eventually approaching the speed of light itself. The engineering challenges are staggering, requiring perfect conversion of matter to energy and near-perfect efficiency, but the physics is sound. Antimatter propulsion represents the ultimate in rocket technology. When matter and antimatter annihilate, they convert 100% of their mass into energy, the most efficient reaction possible in our universe. A spacecraft powered by antimatter could achieve incredible speeds, potentially reaching significant fractions of light speed with relatively modest fuel requirements. The catch? We can currently produce only tiny amounts of antimatter at enormous cost, and storing it safely presents challenges that push the boundaries of current technology. The concept of generation ships offers a fascinating alternative to ultra-high-speed travel. These massive spacecraft would house entire communities for journeys lasting centuries or millennia, with multiple generations living and dying aboard the vessel before reaching their destination. While this doesn't solve the problem of individual humans reaching distant stars within their lifetimes, it does address the broader question of how humanity could spread throughout the galaxy over longer timescales. The engineering challenges of generation ships are staggering. Such vessels would need to be entirely self-sufficient, recycling air, water, and waste with near-perfect efficiency. They would require robust ecosystems, possibly including agriculture and even small forests to maintain psychological well-being over the long journey. The social and psychological challenges might be even greater than the technical ones. Imagine the unique culture that would develop among people who know they'll never see their destination, living only to carry humanity's torch to the stars. But let's return to the tantalizing possibility of reaching distant worlds within a single human lifetime. The key insight from Relativity is that space and time are intimately connected, and high-speed travel doesn't just get you places faster, it literally changes your experience of time itself. This opens up possibilities that seem almost magical, but are grounded in solid physics. Consider the twin paradox, one of relativity's most famous thought experiments. If one twin stays on Earth while the other travels to a distant star at near-light speed, the traveling twin will age much more slowly. Upon reunion, the space-traveling twin might be only a few years older, while their Earth-bound sibling has aged decades. This isn't just theoretical, it's been confirmed with atomic clocks on airplanes and is essential for GPS satellites to work correctly. Speaking of our cosmic neighborhood and the incredible scales we're dealing with, if you're curious about just how vast our galaxy is and where we fit within it, you should definitely check out my video, How Small Are We Inside the Milky Way? It really puts into perspective the mind-boggling distances we're talking about when we discuss interstellar travel, and helps you understand why reaching even nearby stars is such an incredible challenge. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, offers perhaps the most exotic solution to faster-than-light travel. Rather than accelerating through space, this theoretical drive would contract space in front of the spacecraft and expand it behind, creating a warp bubble that could travel faster than light while the ship inside remained stationary relative to local space. The spacecraft wouldn't violate relativity because it's not moving through space faster than light. Space itself is moving. Recent research has made the Alcubierre drive seem slightly less impossible. Harold White at NASA's Eagle Works laboratory has proposed modifications that could dramatically reduce the energy requirements from the mass energy of Jupiter to something closer to the mass of Voyager 1. While still far beyond our current capabilities, this brings warp drive from the realm of pure fantasy into the category of extremely challenging but potentially achievable technology. Wormholes represent another theoretical shortcut through space-time. These hypothetical tunnels through the fabric of space could connect distant regions of the universe, allowing near-instantaneous travel across vast distances. While general relativity permits wormholes mathematically, keeping them stable and traversable would likely require exotic matter with negative energy density, something we've never observed and may not exist. The energy requirements for high-speed interstellar travel are truly astronomical. To accelerate a modest spacecraft to 90% of light speed using conventional propulsion would require more energy than humanity currently produces in an entire year. This is where concepts like solar sails and laser propulsion become attractive. By using external energy sources rather than carrying fuel, spacecraft could potentially achieve much higher speeds. Breakthrough Starshot, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes using powerful lasers to accelerate tiny spacecraft to 20% of light speed. These nanocraft would be no larger than computer chips equipped with cameras and communication equipment. While they couldn't carry humans, they could reach Proxima Centauri in just 20 years and send back humanity's first close-up images of another star system. The psychological and biological challenges of high-speed interstellar travel are as daunting as the technical ones. Extended exposure to cosmic radiation, the effects of prolonged weightlessness, and the psychological stress of isolation would all take their toll on human travelers. The spacecraft would need sophisticated shielding, artificial gravity systems, and closed-loop life support that could operate flawlessly for decades. But perhaps the most profound challenge is philosophical. Travelers on such journeys would be leaving behind everything they've ever known, with no possibility of return. Due to time dilation, even if they could somehow turn around and come back, centuries or millennia would have passed on Earth. They would be true pioneers, carrying human consciousness to the stars, but severing their connection to human civilization forever. The selection and training of interstellar travelers would require unprecedented psychological screening. These individuals would need to be not just physically capable of surviving the journey, but mentally prepared for the ultimate adventure and the ultimate sacrifice. They would be humanity's ambassadors to the cosmos, carrying our hopes, dreams, and genetic heritage to worlds we can barely imagine. Recent advances in hibernation research offer another potential solution. If humans could be safely placed in suspended animation for extended periods, the subjective experience of even very long journeys could be reduced to manageable time frames. Scientists have successfully induced hibernation-like states in animals that don't naturally hibernate, and research into human hibernation for medical applications continues to advance. The discovery of potentially habitable exoplanets has given new urgency to these discussions. Kepler 452b, often called Earth's cousin, sits in the habitable zone of a Sun-like star 452 light-years away. TRAPPIST-1, just 39 light-years distant, hosts 7 Earth-sized planets, several of which might harbor liquid water. These worlds represent genuine targets for interstellar exploration, destinations that could justify the enormous investment required for such missions. The physics of acceleration presents one of the most fundamental constraints on human interstellar travel. While science fiction often glosses over this detail, the human body can only withstand limited acceleration forces before suffering serious injury or death. Fighter pilots can briefly endure accelerations of 9 times Earth's gravity, but sustained acceleration at even 2 or 3 times Earth gravity would be extremely uncomfortable and potentially harmful over extended periods. This acceleration limit directly impacts how quickly we can reach high speeds. If we limit acceleration to a comfortable 1, Earth gravity, the same force you feel standing on our planet's surface, it would take nearly a full year to reach the speed of light, traveling a distance of about half a light year in the process. This means that even with perfect propulsion technology, reaching nearby stars would still require significant portions of a human lifetime just for the acceleration and deceleration phases. However, this constraint also reveals an elegant solution. A spacecraft that accelerates at 1 Earth gravity for the first half of its journey, then decelerates at the same rate for the second half, would provide a comfortable artificial gravity environment for its crew throughout the voyage. The passengers would experience normal weight and could walk around as if they were on Earth, making the psychological challenges of long-duration spaceflight much more manageable. This exploration we're undertaking together, understanding our place in the cosmos and our potential to reach for the stars, is only possible because of curious minds like yours. Make sure to subscribe to the channel and give a thumbs up, because the journey we're on together reveals not just the limits of human travel, but the limitless potential of human imagination and ingenuity. The energy storage and generation requirements for such journeys push the boundaries of known physics. Chemical rockets achieve velocities by ejecting mass at high speed, but even the most energetic chemical reactions provide nowhere near enough specific impulse for interstellar travel. Nuclear fission can release millions of times more energy per unit mass than chemical reactions, but even this falls short of what's needed for significant fractions of light speed. Fusion reactions, which power the stars themselves, offer energies roughly 10 times greater than fission. The hydrogen bomb demonstrates fusion's tremendous power, but controlling this reaction for propulsion remains an enormous challenge. The ITER project in France aims to demonstrate controlled fusion for power generation, but fusion propulsion for spacecraft would require even more advanced technology, including the ability to direct fusion exhaust efficiently for thrust. The interstellar medium itself presents both challenges and opportunities for high-speed travel. Space between the stars isn't truly empty, but contains roughly 1 hydrogen atom per cubic centimeter, along with trace amounts of heavier elements and dust particles. At low speeds, this thin gas is negligible, but at significant fractions of light speed, these particles become like cosmic bullets, requiring massive shielding to protect spacecraft and crew. Paradoxically, this same interstellar medium could serve as fuel for advanced propulsion systems. The bizarre Ramjet concept would use powerful magnetic fields to scoop up hydrogen from space, compress it to fusion densities, and use the resulting energy for both power and propulsion. Such a system could theoretically accelerate continuously throughout its journey, potentially reaching velocities limited only by relativistic effects. The magnetic fields required for a Bussard ramjet would be truly enormous, potentially thousands of kilometers across. Creating and maintaining such fields would require superconducting magnets of unprecedented size and power. Recent advances in high-temperature superconductors and room-temperature superconductor research suggest this might not be forever impossible, though it remains far beyond current capabilities. Laser propulsion offers a near-term path towards significant fractions of light speed for small payloads. The concept is elegantly simple, powerful lasers on Earth or in orbit beam energy to lightweight spacecraft equipped with reflective sails. Since the energy source remains behind, the spacecraft doesn't need to carry fuel, dramatically reducing mass and enabling much higher accelerations. The Breakthrough Starshot project plans to demonstrate this technology with postage stamp-sized spacecraft. Scaling laser propulsion to human-carrying spacecraft presents formidable challenges. The laser power requirements increase with both the mass of the spacecraft and the desired final velocity. A spacecraft capable of carrying humans to nearby stars might require laser installations with power outputs measured in terawatts, roughly equal to the entire world's current electrical generation capacity focused into coherent light beams. Solar sails represent a gentler but potentially more practical approach to interstellar travel. These gossamer-thin reflective sheets harvest momentum from photons, either from the sun or from artificial light sources. While the acceleration is minuscule, solar sails can operate indefinitely without fuel, gradually building up impressive velocities over time. The Icaros mission demonstrated interplanetary solar sailing in 2010, and several follow-up missions have refined the technology. The ultimate solar sail might not be made of conventional materials at all, but of pure energy fields maintained by advanced metamaterials. Theoretical studies suggest that electromagnetic fields could be configured to reflect light more efficiently than any physical material, potentially enabling solar sails with near-perfect reflectivity and virtually no mass. Such devices remain far beyond current technology but aren't forbidden by fundamental physics. Magnetic plasma sails offer another intriguing possibility. These systems would use powerful magnetic fields to interact with the solar wind, the stream of charged particles flowing from the sun. While the solar wind weakens dramatically with distance, a sufficiently large magnetic field could continue to provide thrust throughout the outer solar system and even into interstellar space, where it could interact with the galactic magnetic field. The discovery of dark matter and dark energy has opened entirely new speculative possibilities for propulsion. If dark matter can be manipulated or if dark energy can be harnessed, spacecraft might access energy sources and propulsion methods that dwarf anything based on conventional matter. These remain highly speculative ideas, but they demonstrate how much we still don't understand about the universe's fundamental structure. Recent observations of ultra-high energy cosmic rays have revealed particles with energies that shouldn't be possible according to our understanding of cosmic acceleration mechanisms. These particles somehow achieve energies equivalent to a baseball traveling at 60 miles per hour, concentrated in a single subatomic particle. Understanding how nature creates such energies might reveal new principles that could be applied to spacecraft propulsion. The James Webb Space Telescope has revolutionized our understanding of exoplanets, revealing atmospheres, weather patterns, and chemical compositions of worlds orbiting distant stars. This flood of information about potentially habitable worlds provides new motivation for interstellar travel. Knowing that TRAPPIST-1e has water vapor in its atmosphere, or that K2-18b might have clouds and rain, transforms these from abstract dots of light into genuine destinations worthy of humanity's greatest adventure. The technological convergence required for interstellar travel would likely transform human civilization in the process. The energy systems, materials science, life support technologies, and artificial intelligence needed for such missions would have profound applications on Earth. Developing interstellar travel capabilities might inadvertently solve many of Earth's environmental and resource challenges, creating a positive feedback loop that makes such missions increasingly feasible. Time dilation effects would create profound philosophical and practical challenges for interstellar travelers. While they might subjectively experience only a few years traveling to a distant star, decades or centuries would pass on Earth. They would return, if return were possible, to find that everyone they knew had died, that human civilization had potentially advanced beyond recognition, and that their mission's scientific value might have been superseded by advances in physics and technology that occurred during their absence. The biological challenges of interstellar travel extend far beyond the immediate concerns of acceleration and radiation. The human body evolved over millions of years to function in Earth's specific environment, its gravity, atmospheric pressure, magnetic field, and 24-hour day-night cycle. Removing humans from this carefully tuned environment for extended periods creates a cascade of physiological problems that we're only beginning to understand. Bone density loss represents one of the most serious long-term health challenges for space travelers. Astronauts on the International Space Station lose approximately 1 to 2% of their bone mass per month, primarily from weight-bearing bones like the hips and spine. On a journey lasting several years, even with the artificial gravity provided by constant acceleration, astronauts might lose 20 to 30% of their bone density, creating fracture risks that could be catastrophic in the isolated environment of an interstellar spacecraft. Muscle atrophy presents equally serious concerns. Without the constant resistance provided by Earth's gravity, muscles begin to weaken and shrink within days. The heart itself is a muscle, and studies of long-duration astronauts have shown concerning changes in cardiac function. On interstellar journeys lasting decades, these effects could accumulate to life-threatening levels unless countermeasures are developed that far exceed current exercise regimens used on the space station. Radiation exposure during interstellar travel would be unlike anything humans have previously experienced. Earth's magnetic field and atmosphere protect us from the worst cosmic radiation, but spacecraft travelers would face constant bombardment by high-energy particles that can penetrate conventional shielding. The Apollo astronauts reported seeing flashes of light with their eyes closed, cosmic rays striking their retinas directly. On interstellar journeys, this radiation exposure would continue for years or decades. The psychological challenges might prove even more daunting than the physical ones. The longest single spaceflight in history was Valery Polyakov's 437-day mission aboard the Mir space station, and even that relatively brief journey required extensive psychological support and careful mission planning. Interstellar travelers would face isolation periods measured in years or decades, with no possibility of rescue or early return if psychological problems developed. Sleep cycles represent a surprisingly complex challenge for long-duration spaceflight. Earth's 24-hour cycle is deeply ingrained in human biology through circadian rhythms that affect everything from hormone production to cognitive function. Spacecraft traveling at high speeds wouldn't experience normal day-night cycles, and the psychological effects of eternal, artificial lighting or darkness could be severe. Research with submarine crews and Antarctic researchers provides some insights, but the scale of interstellar journeys is unprecedented. Communication delays would create a unique form of psychological isolation. At the speed of light, radio signals take over 4 years to travel to Proxima Centauri. This means that interstellar travelers would quickly lose the ability to have real-time conversations with anyone on Earth. Emergency support, technical assistance, or even emotional comfort from home would be impossible. The crew would need to be completely self-reliant in ways that no human expedition has ever required. The design of closed-loop life support systems for interstellar travel pushes engineering to its absolute limits. Every breath of air must be recycled, every drop of water reclaimed, and every scrap of organic waste converted back into useful resources. The margin for error is essentially zero. A significant failure in any system could doom the entire mission. Current life support systems on the International Space Station still require regular resupply from Earth, making them inadequate for true long-duration missions. Atmospheric composition becomes critical over extended periods. The space station maintains an atmosphere similar to Earth's, but even small deviations in oxygen, carbon dioxide, or trace gas concentrations could have cumulative health effects over years. The psychological importance of familiar smells, air pressure, and humidity levels shouldn't be underestimated. Humans are incredibly sensitive to environmental cues, and an alien atmosphere could contribute to psychological stress, even if it's technically safe. Food production and nutrition present enormous challenges for multi-year journeys. Stored food degrades over time, losing nutritional value and developing off flavors that could make eating psychologically difficult. Growing food in spacecraft requires understanding plant biology in artificial environments, managing soil or hydroponic systems, and maintaining genetic diversity in seed stocks. The failure of crop systems could quickly become a survival emergency. Water recycling must achieve near-perfect efficiency for interstellar missions. Current systems on the space station recover about 93% of all water, which is impressive but insufficient for truly long missions. Every molecule of water lost to space or locked up in failed equipment represents an irreplaceable resource. Advanced closed-loop systems might need to achieve recycling efficiencies of 99.9% or higher. Waste management extends beyond simple disposal to complete resource recovery. Human waste contains valuable elements like nitrogen and phosphorus that plants need for growth. Developing systems that can safely and efficiently process all organic waste back into useful materials is essential for mission sustainability. This isn't just an engineering challenge, but also a psychological one, as crew members must be comfortable with complete resource recycling. Medical emergencies during interstellar travel would require unprecedented self-sufficiency. The crew would need to handle everything from routine illnesses to major trauma without any possibility of evacuation or specialist consultation. This might require training crew members to perform surgery, dental procedures, and other medical interventions that would normally require years of specialized education. Advanced medical AI systems could provide guidance, but the physical procedures would still require human hands. Genetic considerations become important for multi-generational missions, or missions where crew members might establish colonies on distant worlds. A small crew carries limited genetic diversity, and over multiple generations, this could lead to inbreeding and genetic defects. Mission planners would need to carefully consider the genetic makeup of crews, possibly including stored genetic material or advanced reproductive technologies to maintain healthy genetic diversity. The role of artificial intelligence in interstellar missions cannot be overstated. AI systems would need to monitor and control complex spacecraft systems, assist with navigation and communications, provide medical diagnosis and treatment recommendations, and even serve as psychological companions for isolated crew members. These AI systems would need to operate reliably for decades without maintenance or updates from Earth, representing a level of autonomous operation far beyond current capabilities. Navigation at interstellar distances presents unique challenges. GPS satellites wouldn't exist, and even the positions of stars would appear different due to parallax effects at high speeds. Spacecraft would need to rely on pulsar navigation, using the regular pulses of neutron stars as cosmic lighthouses, or other advanced techniques. The precision required for interstellar navigation far exceeds anything attempted in current space missions. Maintenance and repair capabilities would need to be completely self-contained. Every critical system would require backup systems, spare parts, or the ability to manufacture replacements using onboard equipment. This might require advanced 3D printing capabilities, automated manufacturing systems, and extensive stockpiles of raw materials. The spacecraft would essentially need to be a complete industrial civilization in miniature. The economic scale of interstellar missions boggles the imagination. Conservative estimates suggest that a crewed interstellar mission might cost hundreds of billions or even trillions of dollars, comparable to the gross domestic product of entire nations. Such missions would likely require unprecedented international cooperation, similar to but far exceeding the collaboration seen in projects like the International Space Station or Large Hadron Collider. Resource extraction and utilization during the journey could help offset some costs. Asteroids and comets contain vast quantities of water, metals, and other materials that could be harvested during the journey. Advanced spacecraft might be designed to grow during their missions, using captured resources to build larger habitats, more powerful engines, or additional life support capacity. This approach could transform interstellar missions from one-way trips into true colonization efforts. The concept of relativistic travel opens up destinations that seem impossible at first glance, but become achievable when we factor in time dilation effects. Consider Vega, one of the brightest stars in our night sky, located 25 light-years from Earth. At 99% of light speed, the journey would take just over 25 years from Earth's perspective, but only about 3.5 years would pass for the travelers. They could reach this stellar beacon and still have decades of life ahead of them to explore whatever worlds might orbit this ancient star. Even more exotic destinations become possible when we push closer to light speed. The Pleiades star cluster, that beautiful jewel box of blue stars visible to the naked eye, sits 450 light-years away. At 99.9% of light speed, the journey would subjectively take only about 20 years for the crew, while nearly 5 centuries pass on Earth. These travelers would be true time voyagers, arriving at a stellar nursery where new worlds might still be forming from primordial dust and gas. The galactic center itself, with its supermassive black hole and exotic physics, lies 26,000 light-years distant. At 99.99% of light speed, this journey would feel like just 3 years to the travelers. They could witness phenomena that exist nowhere else in the galaxy, matter spiraling into a 4 million solar mass black hole, creating jets of plasma that extend for thousands of light-years. The energy densities and gravitational fields near Sagittarius A star would provide a natural laboratory for testing the most extreme predictions of general relativity. Antimatter propulsion represents the theoretical pinnacle of rocket technology, offering the highest possible specific impulse by converting matter directly into energy. When a proton meets an antiproton, they annihilate completely, releasing energy according to Einstein's famous equation E equals mc². This complete conversion means that antimatter rockets could achieve velocities limited only by the fuel-mass ratio and the structural integrity of the spacecraft. The practical challenges of antimatter propulsion are staggering. Current worldwide antimatter production amounts to only a few nanograms per year, and it costs roughly $25 billion per gram to produce. A modest antimatter rocket might require kilograms or even tons of antimatter fuel. Scaling up production to these levels would require energy inputs comparable to the total power generation of entire continents, along with storage and containment technologies that barely exist in laboratory prototypes. Magnetic confinement of antimatter requires superconducting magnets operating at temperatures near absolute zero. A failure in these systems would result in instant annihilation of the fuel supply, an explosion that would make nuclear weapons seem like firecrackers. The engineering challenges of creating fail-safe antimatter storage systems for multi-year missions push the boundaries of what might ever be possible with known physics and materials science. Fusion rockets, while less exotic than antimatter systems, offer a more near-term path toward high-performance interstellar propulsion. The deuterium-tritium fusion reaction releases 17.6 million electron volts per reaction, nearly 10 million times more energetic than chemical combustion. A fusion rocket could theoretically achieve exhaust velocities of 10 to 15% of light speed, enabling spacecraft to reach significant fractions of relativistic velocity. Project Daedalus, designed by the British Interplanetary Society in the 1970s, demonstrated the theoretical feasibility of fusion propulsion for interstellar missions. This unmanned probe would have used pellet fusion, tiny fuel pellets compressed by electron beams until they undergo fusion reactions. The design called for 50,000 tons of fuel to accelerate a 50-ton payload to 12% of light speed, reaching Barnard's star in less than 50 years. Ion propulsion, while much gentler than fusion or antimatter systems, offers the advantage of extremely high efficiency and the ability to operate continuously for years. The Dawn spacecraft used ion propulsion to visit both Vesta and Ceres, demonstrating the technology's reliability for long-duration missions. Advanced ion drives using xenon, argon, or even heavier elements could eventually achieve velocities measured in hundreds of kilometers per second. Solar power becomes increasingly inadequate as spacecraft travel farther from the Sun, requiring alternative energy sources for interstellar missions. Nuclear fission reactors offer reliable power independent of solar distance, and several reactor designs specifically intended for space use have been tested. The SNAP series of reactors demonstrated kilowatt-scale nuclear power for satellites, while more recent designs like the SAFE reactor could provide hundreds of kilowatts for advanced propulsion systems. Fusion power generation, distinct from fusion propulsion, could provide the massive energy requirements for advanced spacecraft systems. A compact fusion reactor could power electromagnetic shields against cosmic radiation, support extensive life support systems, and operate high-energy communication systems for maintaining contact with Earth across interstellar distances. The challenge lies in creating fusion reactors small and reliable enough for spacecraft use. Breakthrough propulsion concepts continue to emerge from theoretical physics, though most remain highly speculative. The Alcubierre warp drive would manipulate spacetime itself, contracting space in front of a spacecraft while expanding it behind. Recent modifications to this concept have reduced the exotic matter requirements, though they still exceed anything we could currently produce by many orders of magnitude. Traversable wormholes represent another exotic possibility for faster-than-light travel. These hypothetical shortcuts through spacetime could connect distant regions of the galaxy, allowing near-instantaneous travel across vast distances. However, keeping a wormhole open would likely require exotic matter with negative energy density, something that may not exist anywhere in the universe, and certainly not in quantities useful for spacecraft propulsion. The search for new physics continues to reveal phenomena that could potentially be harnessed for propulsion. Dark energy, which appears to be accelerating the expansion of the universe itself, remains completely mysterious. If this energy could somehow be tapped or manipulated, it might provide propulsion capabilities that dwarf anything based on conventional matter and energy. Similarly, dark matter, which outmasses ordinary matter by a ratio of 5:1, might interact through forces we haven't yet discovered. Quantum vacuum energy represents another speculative but tantalizing possibility. The Casimir effect demonstrates that empty space contains real energy that can exert measurable forces. Some theories suggest that this vacuum energy might be manipulated to provide propulsion, though the energy densities involved are typically very small. More exotic theories propose that the vacuum energy might be much larger than currently observed, hidden by as-yet unknown physics. The development of room-temperature superconductors could revolutionize spacecraft design by enabling powerful magnetic fields without the massive cooling systems currently required. Superconducting magnetic sails could interact with stellar magnetic fields and the galactic magnetic field to provide propulsion across interstellar distances. Such systems might operate indefinitely without fuel, gradually accelerating spacecraft to significant fractions of light speed over periods of decades or centuries. Advanced materials science will be crucial for any high-performance interstellar vehicle. Carbon nanotubes and graphene offer strength-to-weight ratios far exceeding any conventional material, potentially enabling the construction of spacecraft large enough to house substantial crews while still achieving high velocities. Metamaterials with engineered properties could provide electromagnetic shielding, optical systems, and structural components with capabilities impossible using natural materials. The psychological and social dynamics of interstellar crews present challenges as complex as any technical problem. Crews would need to maintain motivation and purpose across journeys lasting years or decades, with no possibility of rescue or early return. The selection criteria for such missions would be unprecedented, requiring individuals who can function effectively in isolation while maintaining the technical skills necessary to operate and maintain incredibly complex spacecraft systems. Communication protocols for interstellar missions would need to account for delays measured in years as spacecraft travel farther from Earth. Crews would gradually transition from real-time communication to time-delayed exchanges, eventually becoming completely autonomous. This psychological transition from being part of human civilization to being truly alone in the cosmos would require careful preparation and support. The discovery of potentially habitable exoplanets has transformed interstellar travel from abstract speculation into concrete mission planning. Proxima Centauri b, orbiting in the habitable zone of our nearest stellar neighbor, represents humanity's first realistic interstellar destination. TRAPPIST-1's 7 Earth-sized planets, several potentially habitable, offer an entire planetary system to explore just 39 light-years away. Kepler 438b, located 470 light-years away, appears to be one of the most Earth-like planets yet discovered. At 99.9% of light speed, this world would be reachable within a human lifetime, offering the possibility of exploring a truly Earth-like environment around another star. The scientific value of such missions would be immeasurable, potentially answering fundamental questions about the prevalence and nature of life in the universe. The technological convergence required for successful interstellar missions would fundamentally transform human civilization in ways that extend far beyond space exploration. The development of closed-loop life support systems capable of operating flawlessly for decades would revolutionize environmental technology on Earth. The materials science advances needed for lightweight, durable spacecraft could transform manufacturing, construction, and transportation. The energy systems required for interstellar propulsion might finally make fusion power practical for terrestrial use, solving many of our environmental and energy challenges. Advanced artificial intelligence systems designed for interstellar missions would need to operate autonomously for years without updates or maintenance from Earth. These AI systems would manage spacecraft operations, monitor crew health, assist with scientific research, and potentially serve as companions for psychologically isolated crew members. The development of such robust, general-purpose AI could accelerate technological progress in virtually every field of human endeavor. Robotic systems aboard interstellar spacecraft would need capabilities far exceeding current technology. They would serve as external maintenance crews, scientific instruments, and potentially as advanced scouts for exploring destination systems. These robots would need to operate in the vacuum of space, repair themselves when damaged, and adapt to completely unknown environments around alien stars. The technologies developed for such systems would find immediate applications in terrestrial manufacturing, exploration, and hazardous environment operations. The question of crew selection for interstellar missions presents unprecedented challenges in human psychology and social dynamics. Traditional astronaut selection focuses on technical competence, physical fitness, and psychological stability for relatively short missions. interstellar crews would need individuals capable of maintaining peak performance for years or decades while isolated from human civilization. They would need to be technically competent across multiple disciplines, psychologically resilient to extreme isolation, and socially compatible for extended cohabitation. Gender balance and reproductive considerations would become critical factors for interstellar crews, particularly for longer missions where the possibility of establishing permanent settlements exists. The crew would need to represent diverse genetic backgrounds to maintain healthy genetic diversity in any potential colony. These considerations raise complex ethical questions about the selection process and the rights and responsibilities of crew members who might become the founders of new human settlements. Cultural preservation becomes a profound challenge for interstellar travelers who might never return to Earth. What aspects of human culture, knowledge, and values should be carried to the stars? How do you compress the entirety of human experience into the limited storage capacity of a spacecraft? Digital libraries could contain vast amounts of information, but the lived experience of human culture, music, art, cuisine, traditions would need to be maintained by the crew themselves across potentially multiple generations. The role of children in interstellar missions raises complex ethical and practical questions. Should children be born aboard spacecraft during multi-decade journeys? How would their development be affected by growing up in artificial environments? Children born in space would never experience Earth's gravity, weather, or natural environments. They would be true citizens of space, potentially better adapted to their spacecraft environment than to any planetary surface, including Earth. Educational systems for spaceborne children would need to provide comprehensive knowledge while operating within the resource constraints of a spacecraft. These children would need to understand both their technological environment and their cultural heritage, preparing them for lives that might be spent entirely in space or as the first generation to colonize alien worlds. The psychological implications of growing up knowing that Earth exists but being unable to visit it would require careful consideration and support. Emergency protocols for interstellar missions must account for scenarios that have no terrestrial equivalent. Equipment failures that would be minor inconveniences on Earth could become life-threatening emergencies when the nearest help is light years away. Medical emergencies would require the crew to serve as their own doctors, surgeons, and medical researchers. Communication failures would cut off all contact with human civilization, leaving the crew truly alone in the cosmos. Backup systems and redundancy would need to be built into every critical spacecraft component. Unlike terrestrial facilities, there would be no possibility of emergency repairs using external resources. The spacecraft would need to carry spare parts, manufacturing capabilities, and repair equipment sufficient for any conceivable failure mode. This level of redundancy and self-sufficiency has never been achieved in any human-built system. The discovery of life around destination stars would transform an interstellar mission from exploration to first contact. Crews would need training in astrobiology, xenoarchaeology, and potentially xenolinguistics. The protocols for investigating alien life would need to balance scientific curiosity with planetary protection concerns. Even microbial life would be a revolutionary discovery, but the possibility of encountering intelligent life would require entirely different mission protocols. Terraforming technologies might be necessary for establishing permanent human presence on exoplanets. Even worlds in the habitable zone of their stars might require atmospheric modification, temperature regulation, or magnetic field generation to become truly livable for humans. The crew of an interstellar mission might need to serve as the advanced team for massive terraforming operations that could take centuries to complete. Resource utilization technologies would be essential for any mission involving surface exploration or permanent settlement. The ability to extract water, oxygen, and metals from alien environments could mean the difference between successful colonization and mission failure. These technologies would need to operate on worlds with unknown geology, atmospheric composition, and potentially hostile environmental conditions. Advanced manufacturing capabilities aboard interstellar spacecraft could enable missions to grow and adapt during their journeys. Three-dimensional printing using materials harvested from asteroids or comets could allow spacecraft to construct additional habitats, manufacturing facilities, or even additional spacecraft. This capability could transform single missions into self-replicating exploration programs that establish human presence throughout nearby star systems. The economics of interstellar missions challenge traditional concepts of cost-benefit analysis. The financial investment required would exceed the gross domestic product of most nations, yet the potential returns, scientific knowledge, technological advancement, and the survival of human civilization are impossible to quantify. These missions would likely require unprecedented international cooperation, similar to but far exceeding the collaboration seen in projects like the International Space Station. Political considerations for interstellar missions would extend far beyond national boundaries. Who has the right to claim exoplanets? How would governance work for self-sufficient interstellar communities? The Outer Space Treaty prohibits national appropriation of celestial bodies, but these laws were written for the solar system. Interstellar space and exoplanets would require entirely new legal frameworks that might not emerge until missions are already underway. Resource conflicts on Earth could directly impact interstellar mission success. The materials needed for advanced spacecraft, rare Earth elements, platinum group metals, and specialized isotopes, are often in limited supply and subject to geopolitical tensions. Securing adequate resources for interstellar missions might require international agreements that guarantee access to critical materials regardless of terrestrial political developments. Technological obsolescence represents a unique challenge for missions lasting decades. Spacecraft systems designed with current technology might become hopelessly outdated during long journeys, while Earth develops far superior alternatives. Communication systems, computers, and scientific instruments that are state-of-the-art at launch might be museum pieces by the time the mission reaches its destination. The psychological impact on Earth's population of successful interstellar missions would be profound. Knowing that humans are living and potentially thriving around other stars would fundamentally change our perspective on our place in the universe. These distant pioneers would serve as symbols of human potential and adaptability, inspiring new generations to look toward the stars with hope rather than resignation. Scientific discoveries made during interstellar journeys could revolutionize our understanding of physics, astronomy, and biology. Direct observations of other star systems, measurements of the interstellar medium, and potentially the discovery of extraterrestrial life would provide data impossible to obtain from Earth-based observations. These missions would serve as moving laboratories, conducting experiments and making observations across light years of space. The development of interstellar communication technologies would be essential for maintaining any connection with Earth during these missions. Laser communication systems might provide higher bandwidth than radio, but would require precise pointing across interstellar distances. Quantum communication might eventually enable instantaneous information transfer, though current understanding suggests this remains impossible for classical information. Navigation systems for interstellar spacecraft would need to operate with unprecedented precision across distances where traditional reference points become inadequate. Pulsar navigation uses the regular pulses of neutron stars as cosmic lighthouses, potentially providing position fixes accurate to within kilometers across interstellar distances. These systems would need to account for relativistic effects, gravitational lensing, and the proper motion of nearby stars. The philosophical implications of interstellar travel extend far beyond technical challenges into the very nature of what it means to be human. Those who venture to the stars would become something unprecedented in our species' history. Humans who have never breathed natural air, felt rain, or seen a sunrise that wasn't artificially generated. They would carry with them the collective knowledge and culture of earth-bound humanity, but their experiences would be so fundamentally different that they might develop entirely new perspectives on existence, consciousness, and our place in the cosmic order. Consider the psychological transformation that would occur during a journey to Wolf 359, a red dwarf star just 7.9 light-years away. At 99% of light speed, this journey would take about 8 years from Earth's perspective, but only 17 months for the travelers due to time dilation. The crew would depart as Earth humans and arrive as something new, people who have experienced the universe in ways no previous generation could imagine, having literally traveled through space and time to reach another star. The cognitive changes resulting from extended exposure to cosmic radiation represent an underexplored aspect of interstellar travel. High-energy particles can penetrate brain tissue, potentially affecting neural function and even personality over time. Astronauts on the International Space Station report changes in their thinking patterns and emotional responses after just 6 months in space. Interstellar travelers exposed to cosmic rays for years might undergo cognitive evolution, developing enhanced pattern recognition, altered risk assessment, or completely new ways of processing information about their environment. Artificial hibernation technology could dramatically expand the range of destinations reachable within a human lifetime. Research with animals that naturally hibernate has revealed that metabolic rates can be reduced by up to 95% while maintaining essential brain and organ function. If humans could safely enter similar states for extended periods, the subjective experience of even century-long journeys could be reduced to weeks or months of conscious time. Recent medical advances in therapeutic hypothermia suggest this might not remain science fiction forever. The development of human hibernation would require solving fundamental problems in human physiology that we don't fully understand. Unlike bears or ground squirrels, humans lack the biological machinery for safely slowing metabolism to hibernation levels. Creating artificial hibernation would require drugs or technologies that could safely shut down non-essential biological processes while maintaining brain function and preventing tissue damage from prolonged inactivity. Cryonic preservation represents a more extreme approach to surviving interstellar journeys, though current technology cannot safely freeze and revive complex organisms. The formation of ice crystals during freezing destroys cell structures, making revival impossible with current techniques. However, research into cryoprotectants and vitrification, turning biological tissue into a glass-like state without ice formation, continues to advance. Future breakthroughs might enable safe preservation of humans for decades or centuries. The psychological preparation for interstellar missions would require unprecedented advances in mental health and human psychology. Traditional astronaut training focuses on relatively short missions with the comfort of knowing that Earth is always visible outside the window and emergency evacuation is possible. Interstellar travelers would need to maintain psychological health while knowing that every day carries them farther from everything they've ever known, with no possibility of return. Virtual reality systems could serve crucial roles in maintaining psychological health during interstellar journeys. High-quality simulations of Earth environments, forests, beaches, cities, could provide psychological relief from the sterile spacecraft environment. These systems could also serve educational functions, allowing crew members to experience historical events, practice emergency procedures, or explore simulated versions of their destination worlds based on telescopic observations. The relationship between Earth and interstellar colonies would be fundamentally different from any previous human migration. Throughout history, even the most distant settlements maintained at least theoretical connections to their homelands. Ships could eventually return with news, trade goods, or additional colonists. Interstellar distances would make such connections impossible except through radio signals that take years to cross space. Communication lag would create unprecedented challenges for governance and cultural continuity. Earth-based mission control would become increasingly irrelevant as spacecraft travel farther from home. By the time radio signals reach a spacecraft orbiting Proxima Centauri, the situations they address would have been resolved years earlier. Interstellar missions would need to be completely autonomous, with crews making life-and-death decisions without any possibility of consultation with Earth-based experts. The scientific return from interstellar missions would justify their enormous cost through discoveries impossible to make from Earth. Direct measurements of the interstellar medium, observations of stellar systems from close range, and potentially the discovery of extraterrestrial life would revolutionize our understanding of the universe. Each interstellar mission would essentially serve as a moving observatory, collecting data across light-years of space. Biosignatures in exoplanet atmospheres represent the most exciting possibility for interstellar missions. Earth-based telescopes can detect the presence of oxygen, methane, or other potential signs of life in distant atmospheres, but confirming biological origins requires much more detailed analysis. An interstellar probe could study atmospheric chemistry with precision impossible from interstellar distances, potentially providing definitive evidence of extraterrestrial life. The discovery of life around nearby stars would transform interstellar missions from exploration to urgent scientific priority. Even microbial life would represent a second genesis, proving that life can arise independently in different stellar systems. Complex life would raise profound questions about intelligence, consciousness, and humanity's role in the cosmos. The protocols for studying alien life would need to balance scientific curiosity with the imperative to avoid contamination in either direction. Planetary protection protocols for interstellar missions would be incredibly complex, as they would need to protect both Earth and destination worlds from biological contamination. Current protocols for Mars missions require extensive sterilization to prevent Earth microbes from contaminating potential Martian life. Interstellar missions would face the additional challenge of potentially bringing alien microorganisms back to Earth, either accidentally or as part of sample return missions. The possibility of discovering intelligent alien civilizations raises questions that extend far beyond science into philosophy, theology, and politics. How would human societies react to definitive proof that we are not alone? What protocols would govern first contact with alien intelligence? The crew of an interstellar mission might become humanity's first ambassadors to alien civilizations, carrying the responsibility of representing our entire species. Advanced manufacturing capabilities aboard interstellar spacecraft could enable missions to establish permanent infrastructure around destination stars. Self-replicating machines could construct space habitats, mining facilities, and additional spacecraft using local materials. This approach could transform single missions into the foundation for permanent human presence in multiple star systems, creating a network of human settlements across nearby regions of the galaxy. The concept of generation ships takes on new meaning when combined with advanced life extension technologies. If human lifespans could be extended to several centuries through medical advances, the distinction between single lifetime missions and generation ships would blur. Crews might live to see their destinations while also raising children who would carry human civilization to even more distant stars. Genetic engineering might become essential for adapting humans to life aboard interstellar spacecraft or on alien worlds. Modifications to enhance radiation resistance, improve efficiency in artificial environments, or enable reproduction in low gravity could make the difference between mission success and failure. These modifications would create new branches of humanity specifically adapted for life in space, raising profound questions about human identity and unity. The economics of interstellar missions might require fundamental changes in how human societies organize resources and make long-term decisions. Democratic governments typically plan in electoral cycles lasting just a few years, while interstellar missions require commitments spanning decades or centuries. Successfully mounting such missions might require new forms of governance specifically designed for managing ultra-long-term projects. Private space companies like SpaceX and Blue Origin have demonstrated that commercial organizations can develop space technology more efficiently than traditional government programs. However, interstellar missions would require investments and timescales that exceed the capacity of any current commercial entity. New hybrid models combining government resources, private innovation, and international cooperation might be necessary to make interstellar travel economically feasible. The technological spin-offs from interstellar mission development would likely transform human civilization even before the first spacecraft departs. Advanced life support systems could solve environmental problems on Earth. Fusion propulsion could provide clean energy for terrestrial use. Artificial intelligence systems designed for spacecraft autonomy could revolutionize manufacturing, transportation, and scientific research. The journey toward the stars might be as transformative as reaching them. Current research in breakthrough propulsion physics continues to explore concepts that could dramatically reduce the time and energy requirements for interstellar travel. The EagleWorks laboratory at NASA has investigated whether modifications to the Alcubierre warp drive concept might be feasible with realistic energy requirements. While still highly speculative, this research suggests that faster-than-light travel might not be forever impossible. The nearest potentially habitable worlds reveal just how far human ambition might realistically extend within a single lifetime using foreseeable technology. Proxima Centauri b, our closest exoplanet neighbor, represents the most accessible target for interstellar exploration. Recent observations suggest this world receives stellar energy similar to Earth and might harbor liquid water on its surface. At 10% of light speed, achievable with advanced fusion or antimatter propulsion, the journey would take 42 years, spanning most of a human lifetime, but remaining within the realm of possibility. Ross 128b, located 11 light-years away, presents another compelling destination. This super-Earth orbits within its star's habitable zone and receives about 1.4 times the stellar flux that Earth receives from the Sun. The planet likely has a substantial atmosphere and could potentially support liquid water. At 15% of light speed, this journey would take 73 years, challenging for a single lifetime mission, but potentially manageable for crews in excellent health with life extension technologies. The TRAPPIST-1 system, 39 light-years distant, offers perhaps the most exciting destination within potential reach of relativistic spacecraft. This system contains 7 Earth-sized planets, 3 of which orbit within the habitable zone. The star itself is a cool red dwarf that could provide stable energy for billions of years, making it an ideal target for permanent human settlement. At 25% of light speed, TRAPPIST-1 would require 156 years to reach, clearly beyond a single human lifetime without revolutionary life extension or hibernation technologies. However, when we factor in relativistic effects, even these distant destinations become more accessible. At 90% of light speed, the subjective travel time to TRAPPIST-1 would be only about 17 years for the crew, while 173 years pass on Earth. This time dilation effect opens up hundreds of potentially habitable worlds within a single human lifetime of subjective travel time, transforming interstellar exploration from impossible dream to engineering challenge. The technical requirements for achieving such velocities reveal the enormous scope of the undertaking. A spacecraft reaching 90% of light speed would possess kinetic energy proportional to the square of its velocity. Even a modest 1,000-ton spacecraft would carry kinetic energy equivalent to the largest nuclear weapons ever built. This energy must be imparted gradually to avoid crushing the crew, requiring propulsion systems that can operate efficiently across a vast range of velocities. Magnetic plasma sails represent one approach to achieving very high velocities without carrying fuel. These systems would use superconducting magnetic fields spanning hundreds of kilometers to interact with the solar wind and interstellar magnetic fields. While the acceleration would be gentle, magnetic sails could theoretically continue accelerating for decades, eventually reaching significant fractions of light speed. The engineering challenges include creating and maintaining magnetic fields of unprecedented size and strength in the harsh environment of interstellar space. Fusion ramjets offer the tantalizing possibility of continuous acceleration using fuel collected from the interstellar medium itself. The concept involves using magnetic fields to scoop up hydrogen atoms from space, compress them to fusion densities, and use the resulting energy for propulsion. Theoretical calculations suggest such systems could accelerate indefinitely, limited only by relativistic effects and the decreasing efficiency of fuel collection at very high speeds. The Bassard ramjet concept faces significant technical challenges that highlight the complexity of interstellar propulsion. The magnetic field required to collect sufficient fuel would need to extend across thousands of kilometers, requiring superconducting coils of enormous size and complexity. The fusion process would need to work efficiently with the very dilute interstellar hydrogen, which has different isotopic ratios than terrestrial fusion fuel. Despite these challenges, the concept represents one of the few theoretical approaches to achieving truly high-performance interstellar propulsion. Breakthrough. Starshot has demonstrated that tiny spacecraft can be accelerated to significant fractions of light speed using powerful lasers. Their concept involves wafer-scale spacecraft accelerated by ground-based laser arrays to 20% of light speed. While these nanocraft couldn't carry humans, they point towards scaled-up systems that might accelerate larger payloads. A laser system powerful enough to accelerate human-carrying spacecraft would require revolutionary advances in laser technology and power generation. The energy requirements for laser propulsion scale dramatically with payload mass and desired velocity. Accelerating a 1,000-ton spacecraft to 50% of light speed would require laser power measured in exawatts, millions of times greater than current global electrical generation capacity. Such systems would likely require space-based power generation using fusion reactors or massive solar collector arrays, representing infrastructure projects dwarfing anything currently under construction on Earth. Solar sails offer a gentler but potentially more practical approach to achieving high velocities over extended periods. Advanced sail materials using carbon nanotubes or metamaterials could achieve area-to-mass ratios far exceeding current technology. Ultra-thin sails spanning thousands of kilometers could harvest momentum from starlight itself, gradually accelerating to impressive velocities without requiring fuel. The challenge lies in creating materials strong enough to withstand the forces involved while remaining light enough for efficient acceleration. The physics of interstellar navigation becomes increasingly complex at high velocities. Stellar aberration causes stars to appear displaced from their true positions due to the spacecraft's motion, while relativistic Doppler effects shift the wavelengths of electromagnetic radiation. Navigation systems would need to account for these effects to maintain accurate course corrections across interstellar distances. Even small navigation errors could cause spacecraft to miss their target star systems entirely. Communication systems for high-speed interstellar missions face unprecedented challenges. Radio signals from a spacecraft traveling at 90% of light speed would be severely Doppler shifted, requiring Earth-based receivers to compensate for frequency changes that could shift signals across the electromagnetic spectrum. The spacecraft's own communication systems would need to account for time dilation effects, ensuring that signal timing remains synchronized with Earth-based expectations. The cosmic microwave background radiation, normally invisible to human senses, would become a significant factor for spacecraft approaching light speed. This relic radiation from the Big Bang would be blue-shifted into visible light and beyond for fast-moving spacecraft, creating a brilliant forward-facing illumination that could interfere with navigation and observation systems. Crews would literally see the universe's ancient light compressed into a blazing spotlight ahead of their ship. High-energy cosmic rays pose increasing dangers as spacecraft velocity approaches light speed. These particles, already dangerous in Earth orbit, would appear even more energetic from the spacecraft's reference frame due to relativistic effects. Shielding systems would need to protect against particles carrying energies equivalent to microscopic bullets, requiring materials and field configurations far beyond current spacecraft technology. The psychological experience of near light-speed travel would be unlike anything in human history. Time dilation would create a profound disconnect between the spacecraft's timeline and events on Earth. Crew members would age slowly while Earth's civilization advances rapidly, making any return journey a journey into an unimaginable future. This temporal displacement would require unprecedented psychological preparation and support systems. Artificial gravity becomes crucial for maintaining crew health during extended high-speed journeys. Rotation-based artificial gravity systems would need to operate reliably for years while maintaining precise structural integrity. The stresses involved in spinning massive spacecraft sections while accelerating at high speeds would require materials engineering advances comparable to those needed for the propulsion systems themselves. Alternative approaches using electromagnetic fields or other exotic physics remain highly speculative. Life support systems for interstellar missions would need to achieve levels of reliability and efficiency that have never been demonstrated in space. Complete recycling of air, water, and organic waste must operate flawlessly for decades without resupply possibilities. Any significant failure could doom the entire mission, requiring redundancy levels that add mass and complexity to an already challenging engineering project. The psychological stress of depending on artificial systems for every breath and drop of water would be immense. Medical care during interstellar missions would require crew members to serve as their own doctors, surgeons, and medical researchers. Advanced diagnostic systems and surgical robots could provide guidance and assistance, but the physical procedures would still require human hands. The possibility of medical emergencies requiring treatments or surgeries that no crew member has been trained to perform present scenarios with no good solutions. Genetic screening and preventive medicine would become crucial for mission success. The discovery of faster-than-light communication, if it proves possible, would revolutionize interstellar mission planning. Quantum entanglement demonstrates instantaneous correlations across arbitrary distances, though current understanding suggests this cannot be used for information transfer. However, our understanding of quantum mechanics continues to evolve, and breakthrough discoveries in quantum information theory could potentially enable real-time communication across interstellar distances. Advanced propulsion concepts continue to emerge from theoretical physics research. The manipulation of dark energy, which accelerates cosmic expansion, might provide propulsion capabilities beyond anything based on conventional matter and energy. Similarly, if dark matter interactions can be understood and harnessed, they might offer new approaches to spacecraft propulsion that circumvent the limitations of chemical and nuclear rockets. The concept of space-time itself as an engineering material opens possibilities that border on science fiction but remain grounded in general relativity. Creating artificial gravitational fields could enable propulsion systems that push against the fabric of space-time itself rather than ejecting reaction mass. Such systems might achieve extraordinary performance while avoiding the fuel limitations that constrain conventional rockets. The search for biosignatures in nearby exoplanet atmospheres has already begun revealing tantalizing hints about potential destinations for interstellar missions. The James Webb Space Telescope recently detected water vapor, clouds, and atmospheric dynamics on K2-18b, a sub-Neptune located 124 light-years away. While this distance places it beyond reach of current propulsion concepts, the discovery demonstrates that we can already identify potentially habitable worlds that might justify the enormous investment required for interstellar missions. Proxima Centauri b continues to fascinate astronomers as our most accessible, potentially habitable destination. Recent studies suggest the planet likely experiences extreme temperature variations due to its tidally locked orbit, with one side permanently facing its star while the other remains in eternal darkness. However, atmospheric modeling indicates that a substantial atmosphere could redistribute heat, creating temperate zones along the terminator line where temperatures might support liquid water and potentially life. The revelation that Proxima Centauri b might harbor magnetic fields strong enough to protect it from stellar radiation has transformed our assessment of its habitability. Red dwarf stars like Proxima Centauri are notorious for producing violent flares that could strip away planetary atmospheres. However, if the planet possesses an Earth-like magnetic field, it could deflect this radiation and maintain a stable atmosphere for billions of years. This makes Proxima b an even more compelling target for humanity's first interstellar mission. Wolf 1061c, located 13.8 light-years away in the constellation Ophiuchus, represents another potentially habitable world within reach of advanced propulsion systems. This super-Earth orbits within its star's habitable zone and receives stellar energy comparable to what Earth receives from the Sun. The planet's larger mass would create stronger surface gravity, but humans could likely adapt to this environment. At 20% of light speed, Wolf 1061c would require 69 years to reach, challenging but potentially manageable for long-lived crews. The concept of multiple destination missions opens up possibilities for exploring entire stellar neighborhoods during extended voyages. A spacecraft capable of reaching significant fractions of light speed could visit several nearby star systems during a single mission lasting decades. Such grand tour missions could explore Proxima Centauri, Barnard's star, Wolf 359, and several other nearby systems, providing comprehensive surveys of our galactic neighborhood. Gravitational assist maneuvers, which have proven invaluable for robotic solar system exploration, could be scaled up for interstellar missions. A spacecraft could use close approaches to massive objects like Jupiter or the Sun to gain additional velocity without expending fuel. More exotic possibilities include gravitational assists from neutron stars or stellar mass black holes, though these would require extraordinary precision in navigation and present enormous risks from tidal forces and radiation. The development of variable specific impulse magnetoplasma rockets represents a near-term advancement toward high-performance interstellar propulsion. These engines can operate across a wide range of specific impulses, optimizing thrust for different mission phases. During initial acceleration from Earth orbit, they could provide high thrust for rapid departure. In cruise mode, they could switch to high specific impulse operation for efficient long-duration acceleration. Such flexibility could enable missions that combine reasonable transit times with manageable fuel requirements. Magnetic field interactions with stellar winds offer another approach to interstellar propulsion that doesn't require carrying reaction mass. As spacecraft enter the heliosphere of destination stars, Magnetic sail systems could harvest energy from stellar winds to provide deceleration for orbital insertion. This approach could eliminate the need to carry fuel for destination arrival, significantly reducing mission mass and enabling higher cruise velocities. The possibility of in-space resource utilization during interstellar transit could transform mission economics and capabilities. Comets and asteroids exist not just in planetary systems, but also in the interstellar medium, ejected from their birth systems by gravitational interactions. Advanced spacecraft could potentially harvest these objects for fuel, water, and construction materials during their journeys, enabling missions to grow and adapt as they travel between stars. Self-replicating spacecraft represent the ultimate expression of interstellar exploration capability. These systems would carry the technology to manufacture copies of themselves using raw materials found at destination systems. A single, self-replicating probe could potentially explore thousands of star systems over cosmic timescales, creating an exponentially expanding wave of exploration that could survey vast regions of the galaxy. While the technology for such systems remains far beyond current capabilities, the concept demonstrates the potential long-term impact of successful interstellar missions. The psychological adaptation required for interstellar travel extends beyond individual crew members to the social dynamics of small, isolated communities. Research with Antarctic research stations, submarine crews, and isolated communities provides insights into how humans adapt to extreme isolation, but interstellar missions would push these limits far beyond any previous human experience. The crew would need to develop new social structures, conflict resolution mechanisms, and cultural practices adapted to their unique environment. Communication protocols for interstellar missions would evolve dramatically as spacecraft travel farther from Earth. Initially, crews would maintain regular contact with mission control, receiving guidance and support from Earth-based teams. As communication delays increase, conversations would become asynchronous exchanges. Eventually, Earth would become a historical reference rather than an active participant in mission operations, forcing crews to develop complete autonomy in decision-making and problem-solving. The role of artificial intelligence in interstellar missions cannot be overstated. AI systems would serve as crew members, advisors, teachers, and potentially companions during the isolation of interstellar travel. These systems would need to operate reliably for decades without updates or maintenance from Earth, requiring levels of autonomous operation far exceeding current technology. The AI systems might need to learn and adapt during the mission, developing new capabilities in response to unexpected challenges or discoveries. Advanced medical technologies specifically designed for interstellar missions would need to address health challenges that have never been encountered in human medicine. Genetic therapies to enhance radiation resistance, tissue engineering to replace organs damaged by cosmic rays, and pharmaceutical systems to maintain mental health during extreme isolation would all be essential. The crew would essentially serve as their own research subjects, testing medical technologies that could benefit all of humanity. The discovery of life at destination star systems would transform interstellar missions from exploration to astrobiology research. Even microbial life would represent one of the most significant discoveries in human history, potentially revealing alternative biochemistries or completely different approaches to organizing living systems. Complex life would raise profound questions about intelligence, consciousness, and humanity's place in the cosmic order. The protocols for studying and potentially interacting with alien life would need to be developed long before missions depart. Planetary engineering technologies might be necessary for establishing permanent human presence on exoplanets. Even worlds in the habitable zone might require atmospheric modification, magnetic field generation, or climate management to become truly livable for humans. The crew of an interstellar mission might serve as advanced teams for massive terraforming operations that could take centuries to complete, transforming alien worlds into new homes for humanity. The economic models for interstellar missions challenge traditional concepts of return on investment. The financial costs would be enormous, comparable to the gross domestic product of major nations, yet the potential returns, scientific knowledge, technological advancement, and the survival insurance of establishing human settlements beyond Earth are impossible to quantify in monetary terms. These missions would likely require new economic frameworks that can account for benefits extending across centuries. International cooperation would be essential for mounting successful interstellar missions, requiring unprecedented coordination between nations, space agencies, and private organizations. The technological challenges exceed the capabilities of any single nation, while the costs would strain even the largest economies. Creating the political and organizational structures needed for such cooperation would be as challenging as solving the technical problems of interstellar travel itself. The timeline for developing interstellar travel capabilities depends on numerous technological breakthroughs that remain uncertain. Fusion propulsion requires mastering controlled fusion reactions that have eluded scientists for decades. Antimatter production needs to be scaled up by factors of billions while reducing costs by similar amounts. Advanced materials, science must deliver substances with properties far exceeding anything currently available. Each of these challenges could take decades to solve, if they can be solved at all. However, the convergence of multiple technological trends suggests that some form of interstellar travel might become possible within the next century. Advances in artificial intelligence, robotics, materials science, nuclear physics, and space technology are all contributing to the foundation needed for interstellar missions. While human interstellar travel might remain beyond our current technological horizon, robotic precursor missions could begin exploring nearby star systems within decades. The search for breakthrough physics that could enable faster-than-light travel continues in laboratories and theoretical studies around the world. Quantum mechanics has already revealed phenomena that seem to violate our intuitive understanding of space and time, and our exploration of fundamental physics continues to reveal new mysteries. While faster-than-light travel remains highly speculative, the history of science suggests that today's impossible technologies sometimes become tomorrow's engineering projects. The development of interstellar travel capabilities would represent a watershed moment in human history, comparable to the development of agriculture, writing, or the scientific method. Successfully reaching other star systems would establish humanity as a truly cosmic species, no longer confined to a single world or solar system. The knowledge gained from such missions would revolutionize our understanding of the universe and our place within it, potentially answering age-old questions about the prevalence of life and intelligence in the cosmos. If you made this far, make sure to hit the subscribe button and give this video a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left, the speed of light and how it breaks our reality. In this video, we dive deep into how the speed of light breaks our intuitive understanding of space, time, and existence. See you there.